Thanks, everyone. Up until now, we've had some very high-level talks, policy, strategy. I'm going to be bringing it down many scales to that of individual forests. So just a bit of background about myself, since I'm new to this audience. Most of my work has been in social ecological systems, primarily in the former apartheid homelands, and I've been working up in Limpopo and Mpumalanga in KwaZulu and Natal, looking at natural resource use and drivers of land cover change. But I decided to change tack and move down to KZN, to the former homeland of KwaZulu, which is indicated here by the white outline, just to look at the different context of change in this homeland, and maybe we can compare it to drivers of change in KwaZulu and Natal. So I knew I wanted to work in KwaZulu, but I wasn't entirely sure what I was going to do. I've got a few things on the go. But I was fortunate enough to meet Ian Rushworth at the SCB conference in France last year. And he was like, oh, you do remote sensing. We need to monitor our forests, our misbelt forests. So I thought, okay, I'm going to fell 2 proverbial trees with 1 axe, and I'm going to look at misbelt forests within the former KwaZulu homeland. So earlier this year, I deployed 2 of my students to go look at natural resource use and dependence on non-timber forest products in the Bulwer area, and the effect that this has on structure and diversity within one of the nearby forests, Maritzburg Nature Reserve. But why are we worried about the misbelt forests, these Afro-temperate misbelt forests? Well, for starters, there's hardly any primary forest left in KZN. Most of them were deforested and logged during the British colonial times, and this is one of the saw pits that you would see in most of the secondary forests around KZN today. So we've lost a lot of our primary forests. And the reason this is a concern is that primary forests hold more than double the amount of carbon than secondary forests do. So in terms of a climate change issue, we're losing the amount of carbon that these forests can sequester. Another reason we're worried about the fate of these misbelt forests is that they often occur in these former homeland areas, or at least close to rural villages who have continued high reliance on natural resources provided by these forests, especially since they occur within a grassland matrix. These forests provide a range of different resources that are necessary for them. So in the context of global change, some of the key drivers of global change, such as land cover change, overexploitation of resources, invasive species, and increasing CO2, these are all factors that are really pertinent to our misbelt forests, and they are factors that are affecting our forests. But unless we actually know what's happening in these forests, we're not going to be able to do anything about it. So we need to be able to measure and monitor the changes that are occurring. Which brings me on to the main focus of this research, which is to create an operational monitoring framework for above-ground carbon storage in Afro-temperate misbelt forests. And I just want to stress the operational monitoring framework. We heard earlier how Ezimvelo's budget has been cut by many millions of rands. So we need something that's actually going to be viable for the long term. It needs to be a workable solution. Now, monitoring of these forests can be a bit tricky for a few reasons. The first is that they span over 400 kilometers of the province, so we've got a really wide expanse of these forests. And they also range in size from 350 meters squared to over 16 square kilometers. So we're dealing with a big extent, different scales, different sizes. Another thing is, and it's the reason we have these forests, but they occur in very tricky terrain. So I don't know how many of you have been into these forests, but I had the pleasure of doing some field work. This is quite tough to walk in. So you've got this tricky terrain that you need to get to. So we've got some issues with monitoring these forests by going into the field. There's a safety issue, both in terms of, falling down a ravine, but also these forests are in very remote areas often, and there's a bit of a personal safety issue. There's a cost issue, there's a time issue just in terms of man hours, and also repeatability. How repeatable and accurately can we measure these forests? So my background's in Earth observation, and my immediate solution to everything is remote sensing. Now, I'm not too sure on the background of a lot of people in the audience here, so just a quick remote sensing 101. There's two types of remote sensing. There's passive and active remote sensing. Passive remote sensing is when you're collecting information about an object using the natural light that's reflected from that object. So the easiest example would be taking a photo with a camera. Okay, I'm taking a photo of you guys, and I would get the light that's reflected back from you. Now, this camera can be held in your hands, it could be mounted on an airplane, or it could be mounted on a satellite. And depending what type of passive remote sensing you're using, you're going to have different scales of images and different extents, different resolutions. Now, this is great, but if we're monitoring forests, these images are 2D, and that's really only going to give us the extent of the forest. But if we want to monitor the carbon in these forests, we're going to need something with a bit more detail. So I mentioned that there's two types of remote sensing. Passive and active. So LiDAR, or light detection and ranging, is a type of active remote sensing. And it's active because the sensor is emitting energy, and in this case it's laser, and it's recording the return signal of that laser pulse. And using an equation of the time taken for the pulse to be returned times the speed of light divided by 2, it gives you the distance to the object, which gives you a height above sea level. This is particularly for airborne LiDAR. For discrete return LiDAR, there's two types. There's discrete return and waveform, but I'm going to be talking about discrete return. You can get up to 4 returns per laser signal. So the airplane's flying over and it's emitting a laser pulse. For every pulse, you're getting 4 different readings coming back. 4 different height readings. The first return is typically the top of canopy return. The last return is a ground return. And then you'll get 2 returns somewhere in between that. And that will depend on the density of the vegetation. So in June this year, I managed to sweet talk my way into getting some LiDAR flown of a forest just nearby here in the Dargle. Some of you might be familiar with it. And they collected LiDAR and aerial imagery over 250 hectares of forest. So here's a little video to show you an idea of what the point cloud looks like. My video making skills aren't fantastic yet, so I apologize if you feel a bit seasick looking at it. But this is just to show you the amount of information we can get from LiDAR and the type of applications, the type of utilities you can use it for. There's a lot of information contained in here. But because of the, this is another example of the point cloud from the forest in the Dargle area. I just want to draw your attention that the resolution of this imagery is around 25 centimeters, which is extremely high. If we take a cross-section through different parts of this point cloud, we can get different structural measurements, and we can look at the differences in the stand compositions between different areas. But because there's a lot of information in the point cloud, we do need to dumb it down a little bit just to make it workable. Height isn't the only thing that's obtained from a LiDAR data set. You can also get the intensity of the return signal, the return number, and the height. And based on these, you can classify the point cloud in different ways. Now, some of the common products that we get from LiDAR are digital surface models and digital elevation models. So digital surface model, imagine just draping a sheet over the top of that point cloud. You're going to get a model of the top of the canopy. And if you do the same thing over the ground returns, you're going to get a digital elevation model. Now, if we subtract the elevation from the surface model, we end up with a canopy height model. And that's what I'm going to be using for my carbon modeling of carbon storage in these forests. So concurrent to the imagery being flown in June this year, I went out into the field and I did 17 field plots. They were 0.05 hectare plots, and they were the standard inventory type of plots that are done in these forests. I measured diameter of the trees, height, species, number of stems. More information than I would need for just the carbon modeling. In order to calculate above ground carbon, I calculated above ground biomass using the wood density by Chevet et al. And converted above ground biomass to above ground carbon using the carbon fraction of 0.47. Now, many studies have been done on the relationship between above ground carbon density, which is on the y-axis, and LiDAR mean canopy height, which is on the x-axis. So this figure is from a study done in tropical forests. And I just want to draw your attention to a few things. The first is that the relationship is different for each region. Okay, so it's very difficult to generalize this, although in the final pane they have come up with a more general model. And it's not a linear relationship. This relationship seems to be almost exponential. So another question I want to ask, as this is actually more of a methodsy, it's in the very much methods phase still, is how well do the tropical forest models translate into the Afro-temperate forest models? Well, so far, not very well. My best fit model was a logarithmic model. I had an R-squared of around 0.5, which, as you'll know, isn't fantastic. And you might notice that my sample size has dropped from 17 down to 10. That's because I had a few issues with some of the plots where I had these massive outliers, which I'm going to go into now. And because of that, I excluded them from my model, which does mean I need to go back into the field. But also I got a logarithmic relationship rather than an exponential one. So some of the issues I had with my data points, this highlights two extreme cases. The rectangle that you can see in these images is the shape of my field inventory plot. And this rectangle has many problems, the biggest of which is that it's got a high perimeter to area ratio. So in the top image, I had low carbon measured in the field, but high carbon estimated from the LiDAR. And that's because the trunks of the trees were outside the plot, but the canopies are inside the plot. So I'm not actually comparing apples with apples. The same thing for the bottom image, where I had high carbon measured in the field, so I had all the trunks in my plot, but the trees grow skew and my canopies occur outside my plot. So one of the ways to combat this is bigger plots and circular plots. So I will be going back into the field to collect more data. This is just an image showing that exact thing, where you have higher error in the models at lower plot sizes. So errors on the y-axis, plot sizes on the x-axis. There's only one study that's got hectare-size blocks, and as much as I'd love to, I think it's a bit too ambitious. Generally, they're around 30-meter radius circular plots. But I did get some results, and I did manage to get a carbon map of the forest. So the top image is just a canopy height image, so just looking at tree height, and the bottom image is the carbon map. It's a heat map, so the warmer colors are higher values and the cooler colors are lower values. And this model looks pretty good, actually. Where the tall trees are, we see high levels of carbon, which is what we expect. So the patterns are right, but as I said, there are issues with the model and with the field work going into it, so I will be going back into the field. But to get back to the original focus of my research, which is creating an operational monitoring framework for monitoring these misbelt forests, let's do a quick reality check. Is LiDAR really the best option for us? Well, no. It really isn't. LiDAR is expensive. I was lucky enough to get this LiDAR donated, but it does cost a couple of $100,000 per flight. So it's costly to collect the imagery, it's costly to process it, there's a high level of expertise that's needed for it. But it's not all in vain. I can use the LiDAR imagery as training data for other two-dimensional imagery that's cheaper or maybe even free. So in the same way that I used fieldwork to validate my LiDAR data, I can use LiDAR to validate lower resolution imagery. So some alternatives that I can start looking at once I've got my model refined is synthetic aperture radar, or SAR. This is also an active form of remote sensing. It's a satellite-based sensor, and instead of lasers, it uses radio waves. It has a 25-meter resolution, though. So the LiDAR I'm looking at has 25 centimeters, and this is now 25 meters. So we're losing a lot of information. But the advantage is we can get historical images, so we can start looking at historical baselines. And because it's three-dimensional, we can still get structural measurements, just on a coarser scale. Another option is high-resolution satellite imagery. This is now two-dimensional, but we might be able to train the imagery on the LiDAR, and this has been done with success in other areas. Another option is drones. Now, drones are the new big thing in science. Everyone seems to have one or know someone who has one. And I do think it's great. You can get aerial imagery flown on a drone. You can also get LiDAR, although fewer people are doing that currently. You can also get stereo paired aerial imagery, so you can start looking at photogrammetry, so you can get a sort of height information from it. But what worries me about drones is the extent of these misbuilt forests. We're looking at over 400 kilometers extent, and a drone currently has to have a person flying it. So I'm not entirely sure how operational that is quite yet. So just a recap on the next steps. As I said, I'm going to go back into the field, and I'm going to collect more data on bigger plots. I'm going to refine my model, more points, and get a lower error associated with my model. And then I'm going to use the LiDAR to train other imagery. And that's it. I'd just like to thank the following people.